Yeah. I'll present the screen now, and you please copy that question. We will solve those two type of questions today. Okay. The question is shared in WhatsApp group also. You can see that. Can you see the question? Hello?
Yes, sir.
Oh, okay. Please copy this question. You'll see. A vertical shaft inward flow reaction turbine. See here he has not given Francis turbine. He has given another way. That is inward flow reaction turbine. That is other meaning of Francis turbine. The other name for the Francis turbine is that. I'll give today what are all the different names we will call, and then those things I'll give today. Okay, so that will be easy for you. Yeah, copy this. A vertical shaft, inward flow reaction turbine, runner develops 12365 kilowatts. That is, it's a power, kilowatts of power, and uses 12 meter cube per second. That is discharge of water. When the net head is 116 meters, the runner has a diameter of 1.5 meter and rotates at 430 RPM. Full stop. Water enters the runner with a velocity of flow. That is, we'll see what is that. I underlined that, that is important. The water enters the runner with a velocity of flow of 10 meter per second and comes out of the runner and enters the draft tube. That is one more word here, draft tube. We'll include the we'll include the concept of draft tube also. You know what you mean by draft tube, right? How, if it is attached to the turbine, how to solve the problem, we will see. With a velocity of 7 meters per second. The difference between the sum and pressure head, sum of the pressure, the difference between the sum of the pressure and potential head at inlet to the runner, and at exit of the runner is 60 meter, 60. Find the velocity and direction of the water at inlet to the runner ಬರೆಯುತ್ತಲ್ಲ ಗೊತ್ತಿಲ್ಲ ನನಗೆ ಅದು ಯಾಕಂದ್ರೆ ಬೋರ್ಡ್ ಮೇಲೆ ಬರೆಯುತ್ತಾರೆ ನೀಟಾಗಿ ಎದ್ರ ಮೇಲೆ ಬರೆಯುತ್ತೆ ಮಾರ್ಕ್ ಆಗಲ್ಲ ಅನ್ಸುತ್ತೆ ನೋಡಿ ಸ್ಮೂತ್ ಇರುತ್ತೆ ಮಣ್ಣು ತಗೊಂಡು ನೋಡಿ ಇಲ್ಲಾಂದ್ರೆ ಆ ಕಡೆ ಇರ್ಬೋದು determine the velocity and direction of the water at the inlet and the runner. Next, blade angle at the inlet. Then you include more. That is not there here. You will include two more unknowns. Sikta? Adu ade. Loss of head in the runner. Next, third one. Loss of head in the runner. Next, hydraulic efficiency. hydraulic efficiency, and specific speed. Hydraulic efficiency and specific speed. I hope you have copied the question, right? Just a minute. Okay. I hope you have copied the question. We will see the data. We'll write down the data. A vertical shaft inward flow turbine. So I'll give the different names for this turbine. You include those things. Okay. This is Francis turbine. Inward flow reaction turbine. This is other name. Mixed flow turbine. This is other name. Okay. So there are, I think probably these three names are different names where he can ask in the different questions. Here, instead of giving directly the Francis turbine, he has given inward flow reaction turbine. That means it is a Francis turbine only, which develops a power P 12,365 kilowatts and uses a Q discharge 12 meter cube per second of water when the head is 116 meters. That is head. The runner has a diameter of 1.5 meter. So I don't know whether it is inner or outer. Just I'll write down D. Based on the value, I'll write 1 or 2. If it is higher, then I'll write as 1. If it is lesser, I'll write as 2. We'll see. Just I'll write 2 for the time being. And rotates at speed 430 rpm. Water enters the runner with a velocity of flow. How much it is? See, velocity of flow is Vf. Entry is 1. Vf1 is equal to 10 meters per second. So this is the first problem where Vf is directly given. In all the problem, he is to give V. He is given Vf in this. And comes out of the runner and enters the draft tube with a velocity of 7 meters per second. I will show you that. What is that? This is V2, 7 meters per second. The difference between the sum of pressure and potential head. So pressure head is P by rho G plus Z. Difference between the sum of potential and pressure head at the inlet to the exit minus of P by rho G plus Z at exit is equal to 60 meters. Find the velocity and direction of the water at inlet. V1 is how much? Alpha 1 is how much? That means velocity at which velocity water is inlet, what is getting inside, and direction. Blade angle at the inlet. Beta is the blade angle, inlet is 1. Then I told you to include 3 more. That is head loss in the runner. Head loss in the runner. I'll write this. What is the head loss? Hydraulic efficiency. And specific speed means NS. So these are all the few unknowns he is asking. Any doubts in writing the data? So just I'll tell you what exactly the arrangement will be. See, this is the reaction turbine, correct? The water will be flowing. And this is called as runner blades. Runner blades. Once the water is doing its work on the runner, what will happen? The water will accumulate at the center and it will discharge. It will discharge through a pipe. It will discharge through a pipe, which is called, and this pipe is called as draft tube. and a portion of the draft tube will be dipped inside the water. Because to maintain the pressure difference, the portion of the draft tube will be dipped inside the water. See, while doing the fluid mechanics lab, in the fluid mechanics lab, while doing a Francis turbine, you concentrate on this, or else you ask your respective faculties to show how the draft tube will be connected to the turbine, how it is going to dip inside the tail race or inside the water, how it is going to dip. You check out. So this is the draft tube. So what is happening? I'll draw the side view of this figure. See, let us assume this is turbine, and what this is penstock. From the penstock, just I'm drawing the side view. From the penstock, water will enter and swirl. It will swirl all around the turbine like this. It will swirl all around the turbine, and that's from the center. The power will generate. That means here there will be a shaft and generator. Okay, this is okay. But the water has to go out. No, where it will go? The water will be connected to a tube called as draft tube. It will be like this. And this draft tube will be dipped inside the water. You check out in the fluid mechanics lab while doing the experiment of this Francis turbine. You come to know how it is connected. Okay. So what is happening? The velocity which is coming out from the penstock we will consider as V1. Correct? After doing its work, the velocity of water which is going will be considered as V2. The velocity leaving will be considered as V2. Right? And velocity which is entering to the draft tube is considered as V3, and the velocity which is leaving here we'll consider as V4. So totally we'll come across 4 velocities. V1 is nothing but right here. V1, velocity of water entering runner. V2, velocity of water leaving runner. V3, velocity of water entering draft tube. See, you may ask, what is the difference between V2 and V3? If there is any leakage losses or something, if there is any losses due loss of velocity due to many reasons, then we will consider 2 velocities, V2 and V3. If there is no loss at all, perfectly everything, though not all the losses are arrested, then V2 will be equal to V3. That you can take from the difference. Just for as a beginning, I'm explaining in detail. Later on, based on the data, we can take V2 is equal to V3, or we'll see what to do. V4 will type it as exit velocity of water from draft tube. Exit velocity of the water from the draft tube. Okay. So I'll give some time. You write down this figure, data, everything. If anybody having doubts, you ask me. Feel free to ask me the doubts if you're having doubts. I hope you are done, right? Okay, you're done with this. What is V1, V2, V3, V4? We'll go for the next sheet. Now, as usual, to solve the problem, assuming high speed turbine. We don't know whether it is a high speed or low speed, what, just we are assuming it at the beginning of the problem. Velocity triangle is as follows. Alpha 1, beta 1 dash, this is beta 1. VR1, VF1, V1. The distance between alpha to beta is considered as U1, and alpha to VF is always considered as VU1 in all the chapters. Similarly, outlet will be right angle triangle. This is beta 2, VR2, V2 is equal to VF2, U2, this is alpha 2. Either you can take any way, anyway it is 90 degree. V2 is 90 degree. So this is the direction of the velocity triangle. So now we'll go to solve one by one. In the data, it was given only one diameter, no? In the data, it was given only one diameter. Other diameter is not given. So whenever, understand this, whenever only one diameter is given, whenever there is one diameter given, instead of giving both the diameters, means this diameter inner and outer, that instead of giving two diameters, if is given one, let us assume this as the bigger diameter. Let us assume, just a minute, I'll highlight it so that it will be easy for you to understand. Yeah, this diameter, let us assume as bigger diameter, that is D1. Okay, assuming that as D1, we'll proceed with the next page, means solution. So what he has given, D1 is, he is asking you to find out D1. Means D1 is given, with the help of that we'll see something. U is equal to pi D1 N by 60. So we know that pi, hence we assume that as a D1. This is not assumed. Whenever only one diameter is given, we have to take it as D1. 430 by 60. You tell me the answer of U1 in meters per second. Even though U1 is not asked, I have determined here. Because it is necessary to proceed further for finding other data. So always remember, we have to find out all the values in the velocity triangle. It will be easy for you. You always find all the values. Here we know only VF1 we know. With this formula, we will come to know U1. And that's all. In the inlet triangle, only we know those two. And in the outlet, what else we know? V2 is known. V2 is equal to VF2, right? So these two values are known. Except this, nothing else is known. Our intention should be finding all these values so that it will be easy for any unknown he asks. Can you tell anyone can tell the answer what is the U1?
33.77.
Very good. 33.77 meters per second. Even though he has not asked, I have done that because because he is asking efficiency, for that it is required. Next. We will find out power also. Means whether power is given, yes. Power is given, we'll see what else can be done with the help of power. Power formula is equal to rho Q G H. Rho Q G H. Efficiency by 1000. If I use this, what else is known? This rho I know. Whether Q I know? Yes, I know Q G H. Efficiency. Yes, directly I can find hydraulic efficiency, right? I can easily find hydraulic efficiency from this equation. But whether he is asking power developed by the shaft or what? Yeah, power developed by the runner. So this is by the turbine. So I can use this as hydraulic. From this equation, try to get hydraulic efficiency. So P by the turbine into 1000 divided by rho is called as 1000. Q is 12, 9.81. H is 116. Directly we got hydraulic efficiency in percentage. This is one formula. Other formula for finding hydraulic efficiency, without the help of power, you can do like this. Sorry. U1 VU1 plus U2 VU2 by GH. So as U2 is 0, this will become 0. So that the efficiency of hydraulic will be U1 VU1 by GH. Either you can find out hydraulic efficiency by this equation or by this. It's you are comfortable. Okay. Just by given data, you can find out hydraulic efficiency if I use a power equation. If you want to use this equation, second equation, I should find out VU1. You find out, definitely you'll get the same answer in both the cases. Only in the form of decimals, you may vary. Answer may vary. But definitely I know the answers will be same. What is the hydraulic efficiency? Anyone?
90.64%.
90?
90.64.
Okay. In this method also, you will get probably near to that. No issue. If you want, you can check out. I am explaining both the methods. Okay. You can use any method to find out the hydraulic efficiency, either that or this. So this is finished. Next, what else is asked? We'll see. I forgot what he's asking. V1, alpha 1, okay. V1 from the velocity triangle I can get basic equation. Alpha 1 I can get, beta 1 I can get. This head loss, hydraulic efficiency is done. Specific speed, we'll see. So let us aim to find out V1, alpha 1 and beta 1. Can anyone tell how to find out the V1 from the velocity triangle? With this known data, what are all the data you know now? You know only VF in the mark, red color I mark here. VF1 I know. U1 I know. I don't know VU1. I don't know V1. So how can I find out V1? Can you tell?
So we'll find VU1, sir.
Okay, very good. Find VU1. How to find out VU1?
From hydraulic efficiency formula.
That's right. From the formula of hydraulic efficiency, you find out the VU1 equation. Or there is one more formula, right? Sorry. There is one more formula. I'll write that formula. P is equal to rho Q U1 VU1 by 1000. So either from this you find out VU1 or hydraulic efficiency is equal to U1 VU1 by GH. So from this you find out VU1. Any one is okay. Both are okay. So that you will get 1 VU1. You tell me the value of what is that VU1 in meters per second.
Thirty point five.
30.5.
In both the methods, you got the same answer. You must get, if there is small deviation, okay, no worry. If it is too much, then you see where the substitution you done from. Okay. So hydraulic efficiency VU1 is done. We will find out V1 now. So I'll mark here what are all the things I came to know. What else I came to know now? This V1. The value of V1 is also known now. So let us find out alpha 1. Sorry, the value of VU1 is known, correct? The value of this VU1 is known. Find out V1. How to go for finding a V1? By using
tan alpha.
Okay.
But find alpha.
If you want tan alpha, again find out alpha there and then find out V1. Yeah, both is asking. He's asking V1 as well as alpha 1. Okay, V1 is equal to, I'll use Pythagoras then. So you tell me what is V1 in meters per second. Similarly, tan alpha 1 is equal to V of 1 by VU1. Find out alpha 1. Tan inverse of V of 1 by VU1. V of 1 is given in the question, no? 10. V1 just now we determined, that is 32.151. Tell me the value of alpha 1 in degrees. And V1, how much you got? I written the answer. You check out whether you got the correct answer or not. This alpha 1 also right. Others also should reply. Use calculator. Print sign just a minute, be online. Yes, did you found the value?
Yes, sir.
Yeah. What are the other values you found out?
Beta 1, sir.
Very good. Beta 1. Can you tell the value of beta 1?
108.06 degree.
Very good. 108.1 degree. So if beta 1 is greater than 90 degree, then you write a note. What is that note? Hence, beta 1 is greater than 90 degree. Therefore, given data corresponds to high speed turbine. Hence, assumed velocity triangle holds good. You write the convincing note. Okay, this is one more way of note writing, or you can write like this. Hence, U1 is greater than VU1. You found out both, no? Data is related to high speed turbine. Hence, assumed velocity triangle holds good. And we can continue further like this. Either you represent with respect to U1 and VU1 or with respect to beta. Both are correct, no issue at all. For as far as possible, you try to represent with respect to U1 and VU1 instead of beta. That is only a thumb rule. You find out with respect to U1 and VU1. But both are correct, no issue. So beta 1 is done. Then what else is asked? After beta 1, something is asked, no? We'll see. V1 is finished, alpha is finished, beta 1 is finished. Yeah, especially this hydraulic efficiency is finished. We'll go for NS, then I'll go for rate loss. Can you write the form? Can anyone tell the formula of specific speed of Francis turbine? Even though we did this in the first chapter, I have not repeated that concept. Hence, we did it in the specific speed for Francis turbine is equal to
N root P by S to the power 5 by 4.
Very good. H to the power of 5 by 4. This is the formula for specific speed. All the values are known. N is known, P is known, H is known. You find out the specific speed in SI units. or you can write in square bracket RPM. What is the value? What's the value?
And 25.6 is I guess.
Hmm? How much? 125 point?
125.6.
Specific speed. You complete that. I'll explain how to do the head. Loss in head. ಕಿರಣ ಇಲ್ಲ ಫಾರಂ ನೋಡಲಿ Satish sir. ಇದು ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ HOD ಮತ್ತೆ ಅನಿತಾ ಮೇಡಮ್ ನೋಡೋರು ಯಾರಿಗೆ ಕೇಳೋರು ಯಾವ ಸಮಸ್ಯೆಗೆ ಹಾಕೊಂಡು okay. Shall I go for head loss?
Yes, sir.
I'll go for the next sheet. Explain head loss. So usually head loss, how you'll find out? By applying the Bernoulli's equation, right? Where to apply the Bernoulli's equation? That we will see. This is turbine. And from the side wave I'm drawing, this is penstock. From the penstock, water will enter. Once the water entered, it will swirl and it will go to the center. From the center, it will go to the draft. This you know. So let us take any section and then we'll try to solve the problem. So I'll take one section here to apply the Bernoulli's equation. One section I'll take here. So this is one section 1 and 1, 2 1 2. Means the energy which is interacting with the turbo machine means a turbine between section 2 1 and 2. If I subtract, where the energy will be more? Energy will be usually high at inlet. Correct? Because of high kinetic energy and potential energy. Energy at outlet will be less. This is true. Energy at the outlet will be less. But what is the Bernoulli's equation tells? Energy at section 1 and section 2 should be balanced. How to write the energy Bernoulli's equation? P1 by rho g plus V1 square by 2g plus Z1. This is the energy available at the inlet. That must be equal to P2 by rho g V2 square by 2g plus Z2. If the pipe is horizontal and both the sides energy is having the same value. But here in this case it won't happen. So what will happen? I'll continue further. What is that continued part? The energy which is available at the section 1 will be equal to the exit energy plus energy utilized by the runner, that is U1 VU1 by G, energy utilized by the runner to produce a power plus head loss. Without head loss, I can write HL. Correct? Loss of head, I can write HL. So now the energy will be balanced. The equation will be balanced. P1 by rho G and V1 square by 2G Z1, that is equal to this right hand side everything. So this indicates, this term indicates energy consumed to generate power. Correct? Next. So he is asking head loss, right? So we'll find out head loss between the inlet and outlet of the runner. HL is equal to P1 by rho G plus V1 square by 2G plus Z1 minus of U1 VU1 by G minus of P2 by rho G V2 square by 2G plus Z2. This is what the final equation where HL he is asking you to find out the HL. So can you tell how to find out HL, whether P1 by rho G is given separately? No. He is given is like this. The combination of pressure and potential head, that is P by rho G and Z. The difference between the inlet and outlet combination of pressure and potential head, that is P1 minus P2 by rho G plus Z1 minus Z2. He has given this combination of this value, which is equal to 60. That is automatically given. We'll use that. HL is equal to P1 minus P2 by rho G plus Z1 minus Z2. What is left out? Plus V1 square by 2G minus V2 square minus U1 VU1 by G. This is left out. You substitute all the values. Now we'll see the combination of these two is 60. So HL is equal to 60 plus what is V1? We determined, no? Somewhere we determined V1.
32.11.
Yes, 32.11 square minus V2. What is V2? I told, no? In the first page I given. There will be V1, V2 exit from the turbine, V3 entry for the rotor. If there is any losses, then V2 and V3 will be different. If there is no loss, then V2 is equal to V3. He has not given anything about the losses between the turbine and the draft tube. So that we'll consider V2 is equal to V3. In that case, what will happen? And V2, what is V2 is given, no? 7 square by 2 into 9.81 minus of U1, 33.77. So VU1 is 30.5 divided by 9.81. So this is separate. This is separate. So take out, find H out, find out the HL, head loss in meters. So tell me the answer.
Minus 39 meters.
Minus 39. How come? Check out. Any other answers? I got different answer. Minus 39 indicates.
5, sir. 5, sir.
It will become around 5 meters.
Yes, sir.
The value is 5 meters. Others, you please check the value. If there is any.
So how did you get the formula for energy consumed to generate power?
This formula. Okay, I'll tell that. You know the Bernoulli equation. There are two Bernoulli equations, right? Means including head loss and without head loss. Oh, sorry. I'll go with the next sheet. See, if there is a pipe, we'll consider this. There is a pipe. Just in FM, you have studied. Just I'll brief out it. 1, 2, section 2. If there is no loss in the pipe between the section and section 2, no loss. What is the Bernoulli equation, right? P1 by rho G, V1 square by 2G plus Z1. That is, this is nothing but a total. I'll write at the bottom what it is. This combination of this is called total energy at section 1. This is the condition what I'm assuming. There is no loss and the pipe is kept horizontal, then P2 by rho G, V2 square by 2G plus Z2. ಏನು ಗೊತ್ತಾ ಅವ್ರ HOD ಸೈನ್ ಹಾಕ್ಸ್ಬೇಕು, ಮ್ಯಾಥ್ಸ್ HOD ಅಲ್ಲ ಅವ್ರದ್ದು ಇಲ್ಲ ಹಾಕ್ಸ್ಬೇಕು, ಅವ್ರದ್ದು ಕೋರ್ಸ್ ಅವರೇ ತಗೊಂಡಿದೆ ಸಬ್ಜೆಕ್ಟ್ ಜೊತೆಗೆ ಅವರು. Okay, this is called as total energy at outlet, total energy at the outlet. When this condition will come, when there is no loss. The second condition will go, if there is some friction in the pipe surface, if there is any friction in the pipe surface, then what you will write? There is a friction in the pipe, the small modification will do in the equation, right? This is V1 by rho G plus V1 square by 2G plus Z1, that is equal to P2 by rho G, V2 square by 2G plus Z2 plus of head loss due to friction. This will write, right? Similarly, now in our case, what is that? In between these two sections, there is one turbine. In between these two sections, we are having a turbine in between the section 1 and section 2. What is the function of a turbine? What is the function of a turbine? To generate the power. How it is going to generate the power? Whatever the energy available at the section 1, it will utilize, the turbine will utilize, and it will generate the power, right? But it cannot utilize completely. It is going to eliminate some power of some head, means some energy of the liquid to the section 2. So what I am going to do now, I am including the friction as well as the power utilized by the runner, difference between section 1 and section 2 by subtracting those. That means if turbine is placed, then the above equation will be P1 by rho G plus V1 square by 2G plus Z1. This is the total amount of energy available at section 1. That is consumed by, first I'll write turbine only, okay? U1, VU1 by G. This is the power consumed by the turbine plus head loss due to friction plus P2 square by 2G plus V2 square by 2G, sorry, P1 by rho G, that's Z2. This is the amount of energy leaving the turbine. So this equation I written that. Is it clear?
Yes, sir. I just wanted to know how you got U1 VU1 by G.
U1 VU1 by?
So the power of the generated by turbine, how you got that formula?
Okay, okay. What is the formula for power or efficiency of the turbine? Efficiency, we'll call it as U1 VU1 by GH, no?
Yes, sir.
This is the equation what I use that. Means how much efficiently that the power, the turbine can utilize that power. Means how much efficiently the turbine can utilize the head which is coming out from the section 1. So from this I written that. Yesterday I told you to submit on question. Have you submitted the answers?
The assignment thing was not there.
No, I forgot to give, but nobody informed me. Today, and I saw, now today morning I saw to evaluate, it was not there, so I thought I'm not given. I'll give. Just a minute. What was the date? Yesterday, 25, no? Fine. I told you to write the question and then you give. Please upload that. Okay, I provided the provision. I given the provision. Just a minute. Thank you. ಈಗ ಇದಕ್ಕೆ ಹೋಲ್ ಪಂಚ್ ಹಾಕ್ತೀವಿ ಸರ್. ಈಗ ನಿನ್ನೆ ಹಾಕಿದ್ರೆ ಹೋಲ್ ಪಂಚ್ ಹಾಕಿ ನಾನು ಜೋಡಿಸ್ಬೇಕು ಎಲ್ಲದಕ್ಕೂ ಮೇಲೆ ನಿನ್ನೆ ಹಾಕಿದ್ರೆ. Have you done? If you're done with that, all of you copy this question.
Can you show the last sheet of the previous question?
ಅದು ನೋಡಿ ಅರೇಂಜ್ ಆರ್ಡರ್ ಇಲ್ಲ, ಅದು ಮೇಲ್ಗಡೆ ಬರಬೇಕು. ಲೋಗೋ ಮಾಡಿ ಅದು ನನ್ನ ಹಿಂದೆ ಮುಂದೆ ಆಗಿದೆ ಪೇಪರ್ಸ್. ಕರೆಕ್ಟ್ ಆಗಿದ್ರೆ ಓಕೆ, ಇಲ್ಲ ಅಂದ್ರೆ ಲೋಗೋ ಮೇಲ್ ಬರಂಗ್ ಮಾಡಿ ಇಲ್ಲಿ. What is the HF? I did not wrote the answer. No? Whether I written the answer? HL is 5. Shall I go for next problem? Yeah, copy this question. See here, the velocity of draft tube exit is given, that is V4. We'll see how to use this V4. Copy that question fast. Thank you. Marketing. Last year. ಇದರಲ್ಲಿ ಈ 15 mm 37 ಇದೆ, ಇಲ್ಲಿ 15 mm 37 ಇಲ್ಲಿ 37 ಇಲ್ಲಿ ಇಂಟು ಹಾಕಿ ಅದೇ ಸಬ್ಜೆಕ್ಟ್ ನೋಡಿ ಇದನ್ನ ಕಳಿಸ್ಬಿಟ್ಟು ರೆಡಿ ಮಾಡಬೇಕು ಅಷ್ಟೇ. ಸಬ್ಜೆಕ್ಟ್ ಕೊಡು, ನೇಮ್ ಆಫ್ ದ ಸಬ್ಜೆಕ್ಟ್ ನೋಡಿ ಟಿಕ್ ಅಳಿಸ್ಬಿಟ್ಟು. Have you done?
One minute, sir.
Pop. See here, yes. We'll see how to do if the velocity of the water exiting the draft tube is given.
So can you repeat
Can
what
you-
you said? Your voice was
Yeah, I was
cracking.
asking so that I'll clarify. See here, I underlined while solving the problem. I'll explain, but still, here I underlined no velocity of the draft tube exit is given. Can you see the previous problem? What I explained here,
Sir, your voice is cracking in between.
the velocity of the water, which is now. Can you hear me?
Yes, sir.
Okay. Here, generally, we'll be having four velocities. I written here. V1 is velocity of the water which is entering the turbine. V2 is velocity of the water which is leaving the turbine. V3 is velocity of the water which is entering the draft tube. Correspondingly, leaving the draft tube is V4. So there are totally four velocities. In the present problem, what I'm showing here, in this problem, we come across with V1, V2, and V3. But I have not taken V3 separately. Correct? What did I done? V3 and V2 I assumed it as same. But in this question, what I am projecting now in this question, he has given velocity of the draft tube exit. Where is the draft tube exit? Can you see here? This V4. Here, the velocity, if I measure here, that is called V4. This velocity it is asking. He is given in this question. I'll explain how to solve if the velocity of the draft tube at the exit is given. Answer to attendance, Sai Sumant,
Present, sir.
Abhishek,
Present, sir.
Abhishek Narayana, Adarsh,
Present, sir.
hey, Abhishek Narayana, are you there? Ajay,
Yes, sir.
Akram, Akshay, Alap,
Present, sir.
Ankit, Ashitesh,
Present, sir.
Vivan, Chinmay, Chandan, Charishma,
Present, sir.
Darshan,
Present, sir.
Ibad, Govindraju, Ruda Jayant, Purushottam, Pritiksha, Jayant,
Present, sir.
Jitin,
Yes, sir.
Chaitanya,
Present, sir.
Ramjit, Kartikeya, Kiran,
Present.
Mohammed Mastanullah, Maizun Umar, Sharan, Narendra, Nihal.
Present, sir.
Yes, sir.
Sir, present, sir. 27.
Okay. 27.
Yes, sir. Kiran.
Okay.
34 also, sir.
Do one thing. All of you type your reverse number in the chat box so that I'll take the attendance there. Only once you type, okay? One class. Okay. I'll stop recording now.